Welcome to our channel. We are so glad you found your way here. Let us help you fall asleep. Let's begin with the ruby crystals of Mars, impact science and planetary gems. Take a slow, deep breath in and release it. Let the weight of the day fade away as we embark on an unhurried, atmospheric journey through the wonders of the cosmos. Your mind is quiet, the universe is vast, and we are ready to explore. Mars 9, the fourth rock from the Sun. Mars presents a striking contrast to its terrestrial neighbors. This planet, often characterized by its reddish hue, derives its color from iron oxide, commonly known as rust. Surface temperatures can plummet to -125 degrees Celsius during nighttime, while daytime conditions can reach a balmy 20 degrees Celsius. Such extremes contribute to the planet's inhospitable environment. Thin atmospheric conditions hinder the presence of liquid water, yet ancient riverbeds and polar ice caps hint at a more hospitable past. Evidence suggests that water once flowed freely across its surface, shaping landscapes and possibly supporting microbial life. Vast plains, towering volcanoes, and deep canyons dominate the Martian terrain, revealing a complex geological history shaped by volcanic activity and erosion. The impact history on Mars has produced remarkable formations, leading to a wealth of scientific inquiry. Meteorite impacts have created craters that serve as windows into the planet's past, exposing layers of rock rich in minerals. Among these minerals, ruby crystals have captured the attention of scientists, exploring their formation and potential significance in understanding planetary processes. Ongoing missions continue to unravel Mars' secrets, investigating its geology and climate. This exploration fosters a deeper understanding of not only Mars itself, but also the broader dynamics of planetary formation and evolution within the solar system. Mars presents a geological history marked by significant transformations. Once, it exhibited a climate similar to Earth, featuring rivers and lakes that carved its surface. Evidence of ancient water flow is visible in the form of dried riverbeds and mineral deposits. These remnants suggest a once thriving environment that supported the potential for life. Over time, volcanic activity reshaped this landscape. Massive shield volcanoes, such as Olympus Mons, stand as towering monuments to the planet's tumultuous past. Their formation results from repeated lava flows, creating layers of basaltic rock. The age of these volcanoes varies, with some showing signs of activity as recent as 2 million years ago, indicating that the geological processes may still be active. Unimpact craters punctuate the surface, each narrating a history of cosmic encounters. These craters range from small depressions to large basins, offering insight into the frequency and scale of impacts that have shaped the Martian terrain. Erosion, driven by wind and perhaps occasional water, has further modified these features, leading to the creation of intricate dust patterns and sedimentary structures. The polar ice caps, primarily composed of water and carbon dioxide ice, undergo seasonal changes, revealing dynamic climatic shifts. This interplay of geological forces illustrates Mars's complex narrative, continuing to intrigue scientists as they unearth its secrets. The formation of Mars can be traced back to the early days of the solar system, approximately 4.6 billion years ago. In this primordial era, protoplanetary disks, composed of gas and dust, coalesced under the influence of gravity. Within these swirling masses, material began to clump together, forming the building blocks of planets. Mars emerged as a smaller terrestrial body, shaped by collisions and accretions within this dynamic environment. This region of the solar system featured a diverse array of elements and compounds, which contributed to the planet's distinct composition. Over time, it became evident that the red planet's surface was sculpted by a combination of volcanic activity and impacts from celestial bodies. These events left behind a legacy of geological formations, including valleys, craters, and ancient riverbeds, each telling a part of its storied past. The presence of iron oxide gives Mars its characteristic hue, while the remnants of ancient water flows suggest a time when conditions may have been more favorable for life. The study of these formations provides vital clues about the planet's evolution, illustrating the complex interactions between its atmosphere, geology, and potential for habitability. Investigating the remnants of this formative period continues to enhance our understanding of planetary development across the cosmos. The evidence of ancient waterways presents a compelling narrative regarding the planet's history. Features resembling river valleys, lake beds, and mineral deposits suggest that liquid water once flowed freely across the Martian surface. Geological formations, shaped by erosion and sedimentation, reveal the once vibrant hydrology that sustained an environment potentially conducive to life. These ancient channels, carved over eons, highlight the dynamic processes that shaped this region. In examining the isotopic compositions of Martian minerals, researchers have identified signs of past aqueous activity. Certain clays and sulfates form only in the presence of water, indicating that liquid existed in significant quantities during specific epochs. The transition from a wetter climate to the arid conditions observed today reflects a profound shift in the planet's atmospheric dynamics. The presence of polar ice caps composed of water ice further emphasizes water's role in Mars's climatic history. Seasonal changes in these caps offer clues to the planet's current temperature and atmospheric cycles. Additionally, subsurface reservoirs may still harbor water, awaiting discovery beneath the inhospitable surface. Understanding these elements provides insight into the mechanisms that govern not only Mars, but also other celestial bodies. It underscores the importance of water as a key factor in planetary processes and potential habitability throughout the solar system. An impact cratering has played a pivotal role in shaping the Martian surface, leaving behind a legacy of geological features that reveal the planet's tumultuous history. The vast plains and towering volcanoes are punctuated by craters of varying sizes, each one a record of a collision with celestial bodies. These formations are not merely scars on the landscape. They offer insights into the timing and frequency of impacts that Mars has endured over billions of years. The oldest craters, located in the southern hemisphere, date back to the Noachian period, approximately 4 billion years ago. These ancient structures suggest a time when the planet experienced intense bombardment, which may have influenced the development of its early atmosphere and hydrosphere. Some of the more recent craters, such as those formed during the Hesperian and Amazonian periods, illustrate a transition in the planet's impact history, reflecting both a decrease in the frequency of large impacts and changes in surface conditions. Craters vary in size, with some measuring several hundred kilometers across, and others being mere meters wide. The study of these formations allows scientists to reconstruct the geological timeline of Mars, providing critical information about its evolution. Understanding this impact history is essential for grasping the broader processes that have shaped not only Mars, but also other celestial bodies throughout the solar system. The science of impact events reveals a complex interplay of forces that have sculpted planetary landscapes across the solar system. Each collision generates shock waves, fracturing the surface and creating craters that serve as geological records on Mars. These craters vary significantly in size and depth, indicating a history of impacts from small meteoroids to massive asteroid strikes. The resulting changes in topography and mineralogy often provide insights into the past conditions of the Martian atmosphere. For instance, the presence of certain minerals, like olivine and pyroxene, can signal alteration processes influenced by impacts. These minerals, along with the distinctive ruby crystals formed under high-pressure conditions, highlight Mars' unique geological history. Impact events also lead to the ejection of materials from the surface. This debris can travel across vast distances, contributing to a dynamic exchange of materials between celestial bodies. The study of ejecta allows scientists to infer the properties of the impacting objects and the conditions present during these violent encounters. The thermal consequences of impacts are also significant, leading to transient heating events that can melt ice and contribute to the formation of subsurface liquid water. Such findings are crucial for understanding the potential for past or present life on the planet. Analyzing these impacts deepens the comprehension of planetary evolution and the ongoing processes that shape the solar system. The physics of crater formation reveals a complex interplay between kinetic energy and surface materials. When an object strikes a planetary surface, it transfers energy, generating shock waves that propagate through the ground. This energy release creates a transient cavity, which may evolve into a more permanent structure as the surrounding material collapses inward. The initial impact results in an explosive event that vaporizes and melts portions of the surface, contributing to the formation of distinct features. The size and morphology of craters depends significantly on the impactor's velocity and mass. Higher velocities lead to deeper and wider depressions, while the composition of the surface plays a crucial role in determining the final structure. On Mars, the presence of volcanic rock, ice, and sedimentary layers introduces additional variables during the impact process. These variations can result in complex layering and unique geological outcomes. Post-impact processes further modify crater landscapes. Erosion, sediment deposition, and volcanic activity can alter the original features, obscuring the impacts over time. The subtle interplay of these forces is observable in Mars's varied terrain, where ancient craters coexist with more recent formations. Each crater serves as a record, preserving evidence of impact events and offering insights into the planet's geological history and evolution. Understanding these processes aids in piecing together the history of our neighboring world. Ruby crystals, formed primarily of corundum, exhibit a remarkable composition that defines their distinctive red hue. The presence of chromium ions within their crystalline structure is critical, imparting the vivid color that characterizes these gems. This mineral, composed of aluminum oxide, displays a hexagonal crystal system, leading to the formation of well-defined facets and a vitreous luster. In Martian geology, the study of ruby crystals reveals insights into the planet's temperature and pressure conditions during their formation. These crystals often arise in metamorphic environments, where intense heat and pressure facilitate their growth. The surrounding matrix can provide context to the geological processes that prevailed, indicating a history of volcanic activity and tectonic movements. The structural arrangement within these crystals plays a significant role in their durability and brilliance. When light penetrates the crystal, it interacts with the atomic lattice, resulting in unique optical properties. This phenomenon contributes not only to the aesthetic appeal of rubies, but also to their scientific importance in understanding Martian conditions. Analysis of ruby crystals from meteorite samples has illuminated the potential for similar formations existing on Mars. Such discoveries encourage further exploration, as they may hold clues to the planet's past environments and the potential for past life forms. These gems serve as a tangible link to ancient geological events that shaped the red planet. Well currents of gemstones on other planets provide intriguing insights into the diversity of planetary formation and evolution beyond Mars. Various celestial bodies within the solar system possess mineral deposits that suggest the presence of precious stones on the Moon. For instance, basaltic lava flows contain traces of olivine, a mineral that can form under high temperatures and pressures. This mineral, while not a gemstone in the traditional sense, hints at the geological processes that have transpired in lunar history. Jupiter's moon Europa presents a different but equally fascinating scenario. Its surface is covered in a thick shell of ice, beneath which lies a subsurface ocean. The potential for gem-like formations exists here, as the unique conditions may allow for the crystallization of minerals within this hidden aquatic environment. The possibility of discovering organic molecules alongside these minerals raises questions about the origins of life beyond Earth. The gas giants themselves, such as Saturn, exhibit atmospheric phenomena that lead to the formation of diamond rain. Under extreme pressure and temperature, carbon particles condense into solid diamonds, creating a form of gem that exists in a state far removed from traditional terrestrial conditions. Each of these occurrences contributes to the understanding of planetary geology and the remarkable variety of natural processes shaping the cosmos. The unique mineralogy of Mars reveals a composition that is both intriguing and complex. Rich deposits of iron oxide impart a distinctive reddish hue, a hallmark of its surface. This iron content is indicative of past environmental conditions that favored oxidation processes, suggesting a history of interaction with water, albeit in its ancient form. These conditions fostered the formation of minerals such as hematite and magnetite, which are abundant in Martian soil and rock. In addition to iron-rich minerals, silicate minerals are prevalent, including olivine and pyroxene. These minerals offer insight into the planet's volcanic activity, with some demonstrating the effects of weathering over eons. The presence of clays indicates that water once played a significant role in shaping this terrain. Such findings provide evidence of a wetter climate, potentially conducive to life. The discovery of sulfates further enhances the mineralogical narrative, revealing a history of acidic environments that may have existed during the planet's formative years. It is within these sulfates that the first signs of ancient water activity can be traced. The analysis of these minerals continues to propel research as scientists seek to unravel the geological history embedded within this rust-colored landscape, piecing together the mysteries of its formation and evolution over millions of years. Historical perspectives reveal a fascination with Martian gems that dates back centuries. Early astronomers, observing the reddish hue through telescopes, speculated about the planet's composition. It was believed that the color stemmed from vast oceans or rich vegetation, a misconception fueled by the romanticism of the unknown. The idea of precious materials on Mars captured the imaginations of many, leading to theories suggesting the presence of crystalline formations. These notions, while misguided, paved the way for later scientific inquiries. In the late 19th century, as technological advancements improved observational capabilities, the focus shifted toward a more empirical understanding of the Martian surface. The advent of spectroscopy allowed scientists to analyze light reflected from the planet, hinting at the presence of various minerals. The excitement surrounding potential Martian gems grew with claims of discovering everything from diamonds to emeralds. Such speculation was often met with skepticism, yet it underscored humanity's enduring curiosity about extraterrestrial geology. The initial theories, though lacking in accuracy, stimulated interest in planetary science and crystallography. This quest for knowledge persisted into the 20th century, as robotic missions began to explore the planet's surface, revealing a wealth of data that would redefine understanding of Martian geology and its potential for harboring crystalline structures. This foundation set the stage for contemporary explorations of the ruby crystals now under scrutiny. The discovery of ruby-like crystals on Mars presents an intriguing avenue of research into the planet's geological history. These striking formations, initially observed in the ancient volcanic regions, indicate conditions that may have been conducive to the formation of similar minerals on Earth. An analysis of their composition reveals a correlation with aluminum oxide and chromium, elements essential for the vibrant red hue commonly associated with rubies. Such findings suggest a unique set of environmental conditions distinct from those typically observed in terrestrial settings. The presence of these crystals raises questions about the past climate of Mars. They form under high-pressure conditions, indicative of significant geological activity. This activity could point to a more dynamic planetary evolution than previously understood. Studying these crystals allows scientists to infer the temperature and pressure conditions present during their formation, providing insights into volcanic processes on the Martian surface. In addition to their geological significance, these ruby-like crystals capture the imagination regarding the potential for life. Their formation may imply that water, or at least water vapor, played a role in their existence, hinting at a more complex history of the planet's habitability. The ongoing analysis of these Martian gems continues to refine our understanding of planetary formation and the dynamic processes that shape celestial bodies. Chemical composition reveals the intricate nature of Martian rubies, primarily composed of aluminium oxide. These gemstones exhibit a distinctive red hue attributed to trace amounts of chromium. This particular element imparts vibrant color through its electronic transitions. The presence of chromium within the crystal lattice indicates the conditions under which these gems formed, highlighting a history of significant geological activity on the Martian surface. Evidence suggests that the formation of rubies on Mars may have occurred through metamorphic processes, where existing minerals were subjected to intense heat and pressure. This alteration transforms precursor materials into crystalline structures, a process that speaks to the planet's volcanic past. In addition to aluminum and chromium, other elements such as iron and titanium can be found, subtly influencing the color and clarity of the rubies. The isotopic ratios of oxygen within these gems offer further insights into the environmental conditions at the time of formation. Variations in oxygen isotopes can inform scientists about the presence of liquid water and the temperature conditions on ancient Mars. This information allows for a deeper comprehension of the planet's climatic history, contributing to a broader understanding of its evolution. Vanessa Rachid's analyzed these Martian rubies. Each discovery enhances the narrative of a planet once teeming with complexity, revealing a world that was unsolved, and perhaps still is, full of hidden treasures. Spectroscopy offers a window into the mineral composition of Mars from vast distances, allowing scientists to unravel the secrets of this distant world without ever setting foot on its surface. By measuring the light reflected off Martian minerals, it becomes possible to identify distinct spectral signatures that correspond to various compounds. This method has been instrumental in revealing the presence of iron oxides, carbonates, and silicates, which collectively paint a portrait of the planet's geochemical landscape. The technique relies on the interaction of light with matter, capturing the unique electromagnetic fingerprints of minerals. These signatures are then compared to laboratory spectra, providing insight into the mineralogy of Martian surfaces. With advancements in spectroscopic instruments aboard orbiters, the analysis of these minerals has become increasingly precise, allowing for detailed mapping of their distribution and abundance across the planet. The findings from this analytical approach suggest that the planet underwent significant geological transformations, hinting at a time when it may have harbored liquid water. Variations in mineral composition across different regions indicate a complex interplay of volcanic activity, weathering, and possibly ancient aqueous processes. Each spectral analysis contributes to a cumulative understanding of Mars, revealing not only its past, but also the potential for future exploration and discovery. In comparing Earth and Martian rubies, significant differences emerge in their formation processes and geological contexts. On Earth, rubies are composed of corundum, a crystalline form of aluminum oxide, colored by trace amounts of chromium. This mineral typically forms in metamorphic and igneous environments, resulting from high pressure, high temperature conditions. Martian rubies present a distinct narrative, formed under a different set of atmospheric and geological conditions. These extraterrestrial gems exhibit variations in their crystalline structures and elemental compositions. The lower gravity and thin atmosphere on Mars contribute to a unique growth environment, influencing how these minerals crystallize and evolve over time. The presence of iron and other transition metals in Martian rubies sometimes leads to a range of hues, diverging from the classic red associated with Earth's specimens. Analyzing these differences sheds light on Mars' geological history, revealing insights into its volcanic activity and the evolution of its crust. This comparative mineralogical analysis not only enhances the understanding of natural processes across planetary bodies, but also informs the search for resources during potential future missions. The characteristics of these rubies could guide scientists in locating areas rich in mineral deposits, emphasizing the importance of studying planetary gems beyond Earth's confines. Each specimen tells a story of its environment, contributing to the broader narrative of planetary evolution. The conditions of heat and pressure play a crucial role in the genesis of ruby crystals on Mars. These gems, formed in the depths of the planet's crust, arise from the interplay of intense temperatures and significant geological forces. The requisite heat, often exceeding several hundred degrees Celsius, is typically generated by volcanic activity or the planet's internal geothermal gradients. Under such elevated temperatures, aluminum and oxygen atoms bond in a specific arrangement, giving rise to the characteristic ruby structure. This arrangement is influenced by the surrounding geological environment, including the presence of impurities, which can alter the color and characteristics of the resulting crystals. Pressure, equally important, acts on these minerals during their formation. It compresses the crystal lattice, enhancing stability and influencing the final morphology as tectonic activity reshapes the Martian landscape. These pressures fluctuate, providing insights into the dynamic processes that govern planetary evolution. The discovery of ruby crystals in Martian regolith not only reveals the history of volcanic events, but also speaks to the potential for similar processes occurring on other celestial bodies. By studying these gems, scientists glean information about ancient environmental conditions, offering a window into the complex interplay of heat, pressure, and mineral formation across the solar system. Meteorite strikes leave profound imprints on Martian geology, shaping the planet's surface in ways that inform our understanding of its history. Each impact generates shock waves, resulting in the fracturing and melting of surrounding materials. This process can create diverse mineralogical formations, including the development of unique crystalline structures within the impact zone. Such alterations reveal insights into the temperature and pressure conditions present during the event. The frequency of meteorite strikes on Mars has significantly contributed to its geological evolution over the course of billions of years. Countless impacts have sculpted the landscape, creating craters that range from small depressions to massive basins. These craters serve as geological archives, preserving evidence of the planet's past and offering clues to its atmospheric and climatic shifts. In some regions, the sedimentary layers exposed by impacts disclose a history of water activity, showcasing ancient lakes and rivers that once flowed across the surface. The minerals formed under these conditions often include clays, sulfates, and other compounds, indicating interactions between water and rock. The discernible patterns in these formations reflect the processes that governed the planet's evolution, extending our grasp of Martian environmental dynamics. Understanding these impacts aids in piecing together Mars's complex geological narrative and its potential for past habitability. Volcanism has played a pivotal role in the formation of these ruby crystals, contributing to the rich geological history of the Martian surface. The intense heat generated by volcanic activity allows for the crystallization of minerals within molten rock, creating the vibrant red hues characteristic of these gems. As magma rises and cools, the conditions become conducive for the formation of various mineral compounds, including corundum, the parent material of ruby ore. The presence of this volcanic activity indicates a dynamic past, where the interior of Mars was once more geologically active than it is today. This activity not only influences crystal development, but also contributes to the alteration of surrounding materials through processes such as melting and metamorphism. The interplay of heat and pressure creates unique environments where these crystals can thrive. In addition to contributing to crystal formation, volcanism affects the atmospheric conditions of Mars. Volcanic eruptions release gases, which may have played a significant role in shaping the planet's early atmosphere. The interaction between volcanic products and surface materials may have further influenced the distribution and concentration of minerals, adding layers to the planet's geological complexity. The significance of these ruby crystals extends beyond their aesthetic appeal. They serve as a tangible link to Mars's volcanic past, providing insights into the environmental conditions that may have existed on this enigmatic planet. Evidence of past magma activity on Mars reveals a dynamic history of geological processes. This region showcases a variety of volcanic features, including ancient lava flows and expansive plains formed by extensive eruptions. The presence of these ruby crystals indicates that magma once surged beneath the surface, carrying with it a rich array of minerals. Volcanic formations, such as shield volcanoes and fissures, offer clues to the intensity and duration of volcanic activity. The morphology of these structures suggests that eruptions varied in scale, with some producing vast sheets of basaltic lava, while others expelled pyroclastic materials. This juxtaposition points to a complex interplay of eruptive styles and magma composition, offering a glimpse into the planet's thermal history. Geochemical analyses reveal that certain minerals, including olivine and pyroxene, are prevalent in the vicinity of these volcanic features. Their presence indicates that the magma underwent varying degrees of differentiation, potentially altering the crystallization process and leading to the formation of unique gemstones like the rubies that encapsulate Mars's volcanic legacy. Studying these remnants of magma activity enables scientists to reconstruct the planet's climatic evolution and assess its potential for hosting past life. This ongoing investigation continues to illuminate the intricate relationship between volcanic activity and the development of Mars's surface landscape. The process of planetary differentiation plays a crucial role in shaping the Martian environment. This phenomenon occurs when a planet's internal structure evolves, leading to the separation of materials based on density. For Mars, its smaller size and lower gravity compared to Earth contributed to a distinct evolutionary path. Denser materials, such as iron and nickel, sank to form a metallic core, while lighter silicates floated to create the mantle and crust. The consequences of this differentiation are evident in the planet's geology. Various minerals, including the ruby-like crystals formed under extreme conditions, can be traced back to the early molten state of Mars. As the planet cooled, these crystals began to solidify, capturing the unique atmospheric and geological conditions present at that time. This region exhibits evidence of past volcanic activity, revealing how the mantle has influenced surface formations and mineral distributions. The presence of these gems serves as a window into the planet's history, indicating periods of intense geological activity. Through analyzing these crystals, scientists gain insights into the temperature, pressure, and chemical environment of early Mars. Such knowledge aids in understanding how these processes have not only sculpted the landscape, but also influenced the potential for past habitability. The interplay between differentiation and volcanic activity continues to shape the narrative of Mars's geological evolution. Crystallization processes on Mars reveal a complex history of mineral formation, influenced by both environmental conditions and geological activity. In the cooler regions of the planet, these processes occur under the influence of lower temperatures, leading to the formation of various minerals, including the striking ruby crystals. These gems emerge from the cooling and solidification of molten rock, where specific elements and compounds interact, resulting in the unique hues observed in Martian specimens. The presence of magnesium, iron, and chromium plays a critical role in the development of these vibrant crystals. Their crystallization typically occurs within igneous rocks, where temperature and pressure create ideal conditions for the growth of such minerals. This region, characterized by its diverse landscape, showcases the remnants of ancient volcanic activity, further influencing the distribution and abundance of ruby crystals. In areas where water once flowed, the potential for alteration processes increases, allowing for the interaction of minerals with liquid, which can lead to secondary crystallization. The findings suggest a dynamic interplay between the planet's geological history and the formation of these gems. While the Martian atmosphere is thin, it does not inhibit the crystallization process. Instead, it adds to the unique characteristics of the minerals formed. The ruby crystals stand as a testament to the planet's intricate past, encapsulating the essence of Martian geology. The study of Martian meteorites reveals critical insights into the planet's formation and evolution. These fragments, ejected from Mars by ancient impacts, serve as a bridge between two worlds. Their journey through the solar system offers a unique glimpse into the Martian environment, preserved within the confines of these extraterrestrial rocks, composed of minerals characteristic of Martian geology, such as olivine and pyroxene. These meteorites provide invaluable information about the planet's crust and mantle. Isotopic analyses reveal the age of these samples, indicating that many originated during a time when liquid water may have existed on the surface. This supports theories of a once habitable environment on Mars, where conditions could have supported life. Radiometric dating techniques further establish timelines for volcanic activity, suggesting that Mars experienced significant geological changes over millions of years. Each meteorite carries with it the potential to unravel mysteries, such as the presence of organic compounds, which could indicate past biological processes. In laboratories on Earth, Sophisticated instruments analyze these interplanetary visitors, allowing scientists to piece together the climatic and geological history of Mars. The research continues to enhance the understanding of not only Mars, but also the broader context of planetary formation across the solar system. With each discovery, the narrative of this distant world unfolds, connecting terrestrial and extraterrestrial realms. The implications of Ruby discovery extend beyond mere geological interest. These vibrant minerals indicate a history of intense conditions, suggesting that this region once experienced significant heat and pressure. Their formation points to a dynamic past where volcanic activity may have played a crucial role. Such activity contributes to a deeper understanding of the planet's crust and the potential for habitability. These findings inspire questions about the presence of water, a fundamental element for life. The geological processes responsible for creating these gems might have also facilitated aqueous environments in the distant past. The interaction between minerals and liquid water could have spurred chemical reactions critical for the emergence of life. This connection elevates the significance of ruby deposits, as they may serve as markers for ancient aqueous systems. Research into these gems further informs astrobiological models. The presence of ruby crystals could imply that other minerals associated with biological processes might exist in nearby strata. Each specimen becomes a beacon for understanding the potential for past life forms, as they reveal clues about the environmental conditions that prevailed. The intricate interplay of geology and astrobiology on Mars is underscored by these discoveries. The study of ruby crystals not only enriches our understanding of planetary geology, but also expands the search for life beyond Earth. Mars rovers serve as essential tools for mineral exploration, meticulously designed to traverse the planet's varied terrain. Their advanced instrumentation allows for detailed analysis of surface materials, revealing the rich mineralogy present in this alien landscape. Equipped with spectrometers, these mobile laboratories can identify mineral compositions from afar, providing crucial data on the geological history of Mars. These rovers navigate an environment characterized by dusty plains, rugged canyons, and ancient riverbeds. They collect samples from diverse geological formations, sending invaluable information back to Earth for further analysis. Each sample offers insights into past conditions, enabling scientists to reconstruct the climatic evolution of this planet. The exploration extends to detecting specific minerals known to form under various conditions, including the elusive presence of water. Water's history on Mars is pivotal, as it informs the potential for life and the habitability of this once lively world. In their quest, rovers analyze the unique features of their surroundings, including intriguing rock formations that may hold clues to past volcanic activity or sedimentation processes. Through their relentless pursuit, these robotic explorers reveal the intricate narrative etched into the Martian landscape. Each discovery contributes to a broader understanding of planetary evolution, paving the way for future missions and the ongoing quest for life beyond our home planet. The Curiosity rover, an emblem of human ingenuity, traverses the Martian landscape, equipped with an array of scientific instruments. Its mission extends beyond mere exploration. It seeks to uncover the geological history embedded within the reddish terrain. Each drill hole and soil sample provides critical insights into the processes that shaped this planet, revealing the intricate history of water and mineral formation. Among its findings are the elusive ruby crystals identified within the Martian rocks. These gems, a result of high-temperature conditions and unique chemical environments, offer an intriguing glimpse into the planet's volcanic past. Their presence suggests that Mars experienced episodes of intense geological activity, possibly linked to the ancient presence of water. This region, marked by ancient riverbeds and sedimentary layers, serves as a key focal point for scientists. The interaction between water and minerals could elucidate how life might have existed on Mars. Each sample collected by the rover is meticulously analyzed, revealing the potential for organic compounds and the conditions necessary for life. The ongoing exploration raises questions about the formation of these gems and their significance in understanding not only Mars but also terrestrial processes. The Curiosity rover stands as a testament to the enduring human spirit, pushing the boundaries of knowledge in the quest to uncover the secrets of our solar system. The Perseverance rover, a sophisticated extension of human inquiry, embarks on its mission to explore the Martian surface with enhanced mineralogical capabilities. Equipped with advanced instruments, it analyzes the composition of rocks and soils, revealing the mineralogical diversity prevalent in this arid landscape. This exploration illuminates the geological history of Mars, offering insights into its past environments and the potential for ancient life. The rover's laser-induced breakdown spectroscopy tool allows for precise elemental analysis, identifying key minerals that contribute to the understanding of Martian geology. These analyses uncover variations in mineral types, such as basalt, clay, and sulfates, each indicating different formation processes and environmental conditions. The identification of these minerals leads to broader implications about the planet's hydrological history. The search for organic compounds has become a significant aspect of its mission. Through careful examination, the Perseverance rover seeks signs of past biotic activity, potentially preserved within mineral matrices. This research not only enhances knowledge of Mars, but also serves as a model for understanding planetary processes across the solar system. The rover's journey through rugged terrains and ancient river deltas further aids in unraveling the complexities of Martian geology. Each discovery is a piece of a larger puzzle, contributing to the ongoing narrative of Mars and its enigmatic history. Remote sensing techniques have become vital for identifying the presence of ruby crystals on Mars. These methods utilize a range of electromagnetic waves, Hafthazam up beta. The thousands of ruby crystals on Mars. These methods utilize a range of electromagnetic waves, allowing scientists to analyze surface materials from significant distances. Hyperspectral imaging, for instance, captures the subtle variations in light reflected from the Martian surface, revealing mineralogical compositions that might otherwise remain concealed. The data collected can indicate the presence of corundum, the mineral from which rubies are formed, by detecting specific spectral signatures. This approach aids in locating regions where geological processes may have concentrated these precious stones. Thermal infrared measurements further enhance this analysis, permitting the investigation of temperature differences that correlate with varying mineral properties. LIDAR technology, capable of mapping surface topography with remarkable precision, provides additional context about potential gem-bearing areas. By revealing the shape and structure of the landscape, it helps scientists prioritize locations for ground-based exploration. The synergy of these techniques allows for a comprehensive understanding of Mars's geological history, particularly in areas where volcanic activity and sedimentation may have played crucial roles. Each dataset builds upon the last, gradually illuminating the processes that could have led to the formation of these planetary gems, enriching our understanding of both Mars and the broader dynamics of gemology within the solar system. Analyzing Martian soil samples reveals a complex interplay of mineral composition and environmental conditions. The presence of specific crystalline structures indicates a history shaped by volcanic activity and aqueous processes. These samples, collected from various regions, showcase a spectrum of gemological content, including the distinct ruby crystals that have captured scientific interest. The examination of these samples employs advanced spectroscopic techniques, allowing researchers to identify unique spectral signatures that correspond to various minerals. This method provides critical insights into the geological history of the Martian surface. In particular, the conditions under which these ruby-like crystals formed become apparent, suggesting episodes of intense heat and pressure, followed by cooling phases that allowed for crystallization. Intriguingly, the distribution of these crystals across the Martian landscape hints at ancient hydrothermal systems that may have facilitated their emergence. This region of Mars, characterized by its rugged terrain, offers a glimpse into the planet's volcanic past, where molten rock interacted with water, creating the ideal environment for gem formation. These findings challenge previous assumptions about Martian geology, emphasizing the potential for more complex processes at play. With each analysis, the narrative of Martian soil becomes increasingly nuanced, revealing a rich history that intertwines planetary evolution with the formation of exquisite gems. The quest for understanding continues to unfold. Dust storms on Mars play a significant role in shaping its surface, influencing both erosion processes and the exposure of geological features. These storms, which can envelop vast regions of fauna, are capable of transporting fine particles across great distances. The relentless movement of this abrasive material gradually wears down rock formations, smoothing their contours and revealing hidden structures. The dynamics of these storms create a unique environment where elements buried beneath layers of sediment may become exposed over time. This exposure is vital for revealing the planet's geological history, including the presence of rare minerals and gemstones. The shifting sands and dust can unearth ruby crystals, often nestled within the bedrock, displaying their vibrant hues against the stark Martian landscape. Observations of these phenomena suggest that the seasonal cycles of dust storms contribute to a gradual yet constant reshaping of the terrain. With each storm, new surfaces are revealed, while older ones are eroded away. This ongoing process not only affects the physical landscape, but also offers insights into the mineralogical composition of Mars. The implications for future exploration are profound, as understanding the behavior of dust storms could guide missions aimed at unearthing these planetary gems, providing clues about the planet's past and the processes that have shaped it. Crater age determination serves as a fundamental lens through which the history of this region can be perceived. Each impact event leaves a distinct mark, creating craters that vary in size and depth, reflecting the energy and velocity of the impacting bodies. The analysis of these formations reveals information regarding the geological timeline of Mars, offering insights into its climatic and environmental evolution. Dating these craters involves a detailed examination of their morphology and the surrounding regolith. The presence of superimposed craters indicates a relative age, while the degree of erosion and degradation provides hints about the planet's atmospheric conditions over time. This understanding is critical for piecing together the sequence of events that led to the formation of crimson-hued minerals, such as the ruby crystals, during the planet's formative years. The processes of gem formation are intricately linked to the impact events that shaped the Martian surface. Shock pressure and temperature during impacts can lead to the crystallization of minerals, resulting in the creation of unique specimens. These gems, formed under extreme conditions, encapsulate valuable data regarding the elemental composition and thermal history of Mars. Each crystal embodies a fragment of the planet's narrative, waiting to be uncovered by future missions. Through meticulous exploration, the secrets of this enigmatic world may gradually be revealed. The preservation of crystals in impact sites offers unique insights into Martian history. Crater formations, resulting from collisions with celestial bodies, provide ideal conditions for the survival of these geological specimens. Intense heat and pressure alter the surrounding materials, creating environments where crystalline structures can thrive. These formations often serve as time capsules, encasing ancient minerals and organic compounds that may have once existed. The interplay between impacts and the Martian atmosphere plays a crucial role in the preservation of these crystals. The thin atmosphere allows for less erosion, enabling crystalline structures to remain relatively intact over eons. In contrast, Earth's more dynamic environment erodes similar formations more rapidly. This stability presents an opportunity to study the crystallization processes that occurred millions of years ago. Distinct varieties of ruby crystals, formed under specific conditions, can be found amidst the debris of impact events. Their unique chemical compositions reveal information about the Martian surface and subsurface. By analyzing these gems, researchers can infer the planet's past conditions, including temperature fluctuations and volcanic activity. In the quest to unravel the mysteries of Mars, these preserved crystals serve not only as evidence of ancient processes, but also as a bridge connecting the present with a distant dynamic past. Each specimen tells a silent story of transformation and survival in an unforgiving landscape. Crater size plays a crucial role in the formation of these remarkable gems. Larger impacts generate intense pressure and heat, conditions that facilitate the crystallization of minerals from the surrounding rock. This process can result in the formation of ruby crystals, which emerge from the transformed debris of the impact event. The sheer force of such collisions reshapes the Martian surface, creating a variety of geological features, including expansive basins and rugged peaks. Smaller craters also contribute to the gem formation process, albeit in more subtle ways. These impacts may not reach the extreme temperatures of their larger counterparts, yet they can fracture the subsurface material, allowing for the movement and concentration of mineral. Over time, repeated smaller impacts accumulate, creating a mosaic of geological activity that enriches the local environment. Each impact site holds potential for discovering unique mineral compositions, reflecting the planet's dynamic history. This intricate relationship extends beyond mere geology. The presence of rubies and other minerals can indicate past conditions that favored the crystallization process. By studying these gems, scientists glean insights into the climatic and geological evolution of Mars. The interplay between impact energy and mineral formation reveals the complexity of this otherworldly landscape, where time and forces of nature intertwine to create exquisite natural artifacts. Mars' climate history has played a pivotal role in shaping its geological features and the formation of unique mineral specimens. The planet's ancient atmosphere, once thick and capable of sustaining liquid water, underwent significant changes due to a variety of factors, including solar wind and loss of magnetic field. This transition from a warmer, wetter environment to the current cold, arid landscape has left indelible marks on its surface. Gradual erosion and sedimentation processes have sculpted the terrain, revealing layers of rock that hold clues to the planet's climatic past. Impact events add another dimension to this geological narrative, creating shockwaves that can alter the structural integrity of minerals. The resultant heat and pressure from these collisions can lead to the crystallization of specific gems, such as the striking ruby crystals found in Martian regolith. These gems, formed under extreme conditions, exhibit unique attributes that reflect their origins. The interactions between the minerals present in the soil and the forces unleashed during impacts contribute to the formation of intricate crystal structures. Evidence of volcanic activity further complicates the landscape, introducing additional minerals and altering pre-existing ones. Understanding these processes not only unveils the secrets of Martian geology, but also enriches our comprehension of gem formation under extraterrestrial conditions. The atmosphere of Mars, characterized by its thin composition, plays a significant role in determining mineral stability. With an average pressure less than 1% of Earth's, the conditions here create a unique environment for mineral preservations. This reduced atmospheric pressure limits the extent of weathering processes that typically alter surface minerals on more humid planets. Carbon dioxide dominates this thin atmosphere, with traces of nitrogen and argon. The presence of carbon dioxide influences the formation of carbonate minerals, which exhibit distinct stability patterns. In this region, the interaction of carbon dioxide with surface materials can lead to the formation of various carbonates, which are vital for understanding past aqueous activity. Temperature fluctuations further contribute to mineral stability. The Martian surface experiences extreme thermal variations, from frigid nights to relatively warmer days. Such conditions can lead to the expansion and contraction of minerals, potentially affecting their structural integrity. Wind erosion, while limited, still plays a role in shaping surface features and redistributing fine particles. This process can expose subsurface minerals to the thin atmosphere, initiating new chemical reactions. The interplay between these atmospheric factors and mineral composition reveals a complex relationship that shapes the Martian landscape and its geological history. Insights into this dynamic environment offer valuable perspectives on planetary evolution and the potential for resource exploration. Shield volcanoes play a pivotal role in the formation of unique minerals, including the striking ruby crystals observed in Martian geology. Characterized by their broad, gently sloping profiles, these volcanic structures allow for the steady outpouring of basaltic lava, creating conditions conducive to crystal growth. This environment fosters the gradual cooling of magma, a process that facilitates the formation of intricate mineral structures. The low cooling associated with shield volcanoes permits the crystallization of various elements, including aluminum and chromium, essential components in the formation of ruby crystals. As magma ascends through the crust, it interacts with surrounding materials, enriching the melt with trace elements that contribute to the vibrant hues of these gems. The specific conditions within these volcanic systems can result in the development of significant crystal deposits, which become a focal point for geological inquiry. Studies of these formations provide clarity on the thermal and chemical processes underpinning mineral genesis. The longevity of shield volcanoes, often spanning millions of years, allows for extensive periods of crystallizations, leading to the accumulation of valuable deposits. Analyzing the distribution and characteristics of ruby crystals in Martian shield volcanoes not only enhances the understanding of local geology, but also hints at broader implications for planetary resource utilization and the search for extraterrestrial materials. The presence of ancient lakes on Mars plays a pivotal role in the formation of ruby crystals. These bodies of water, once abundant on the surface, provided a unique environment for the crystallization of minerals. Over time, sediments accumulated in these lakes, creating a rich chemical milieu conducive to gem development. The interaction between water and volcanic activity likely contributed to the synthesis of aluminum-rich minerals essential for ruby formation. Sedimentary deposits reveal that these lakes fluctuated in size and salinity, influencing the mineral composition. Geological evidence indicates that episodic flooding and drying cycles may have facilitated the concentration of essential elements. The resulting conditions led to the nucleation of crystalline structures, resulting in the formation of rubies within the sedimentary layers. The remnants of these ancient lakes, now arid and desolate, serve as markers of a once vibrant geological past. They provide insight into the climatic conditions that prevailed, suggesting a dynamic interplay between water and geological processes. This understanding extends to potential strategies for resource extraction, where the remnants of ancient lakes may indicate locations rich in valuable minerals. Identifying these regions on Mars may inform future exploration missions, revealing not only the planet's geological history, but also the potential for resource utilization in human endeavors. The study of these gems unfolds a narrative of resilience in an otherwise harsh environment. Mars displays a striking contrast between its highlands and lowlands, a testament to its geological diversity. This region, characterized by rugged terrains, features ancient volcanic rock formations and heavily cratered surfaces, remnants of a time when the planet experienced intense geological activity. Elevated areas, known as the Southern Highlands, exhibit a complex history of impacts, erosion, and tectonic processes, revealing layers of rock that tell tales of a once dynamic world. In stark contrast, the lowlands, particularly the northern plains, are smoother and younger in appearance. These vast expanses, shaped by ancient oceans and sedimentary processes, highlight a different chapter in Mars' geological narrative. The transition between the highlands and lowlands is marked by a distinct boundary, often referred to as the dichotomy boundary, which signifies a shift in the planet's evolution. The presence of these contrasting features offers insights into the conditions that shaped Mars over billions of years. The highlands retain evidence of a harsher, more tumultuous past, while the lowlands suggest a time of relative calm, possibly accommodating bodies of water. Understanding this division allows scientists to piece together the complex history of the Martian surface, offering clues about its potential for past life and the processes that have shaped its environment. This exploration continues to enhance our comprehension of planetary evolution. The surface of Mars reveals a history marked by both violent impacts and gradual processes. The ruby crystals, formed under extreme conditions, provide a unique insight into this evolution. These gemstones, rich in aluminium oxide, emerge from the intense heat generated during collisions with celestial bodies. Each crystal serves as a record, encapsulating the environmental conditions present during its formation. Geological formations across the Martian landscape exhibit evidence of past volcanic activity and sedimentary layers, which further inform our understanding of its surface evolution. The interplay between impacts and volcanic events shaped the terrain, leading to a diverse array of mineral deposits. These deposits not only include ruby but also other silicate and oxide minerals, indicating a complex geological history. The analysis of these gems allows scientists to deduce the thermal and pressure conditions that once prevailed. By examining the inclusions within the crystals, researchers can ascertain the presence of ancient water, an essential component for the potential of life. As these studies progress, they continue to reveal the intricate relationship between impact events and the development of minerals in Martian geology. This meticulous investigation of ruby crystals and their surroundings paints a clearer picture of Mars as a once vibrant world, rich in geological processes that have shaped its current state. The findings contribute significantly to our understanding of the planet's past and its potential to harbor life. The similarities and differences between Mars and Earth reveal intriguing insights into gem deposits across these distinct worlds. On Earth, geological processes such as plate tectonics, volcanic activity, and erosion have shaped a rich variety of gemstones, including rubies and sapphires. These processes continuously recycle materials, creating an environment conducive to the formation of such minerals. In contrast, the Martian landscape offers a starkly different narrative. The absence of plate tectonics and the planet's relatively static geological history have resulted in a more limited variety of minerals. The ruby crystals discovered on Mars, formed under specific conditions of temperature and pressure, suggest a unique story of formation and alteration. The Martian atmosphere, characterized by its thinness, influences the preservation of these crystals, allowing them to withstand eons of exposure to harsh conditions. Factors such as ancient volcanic activity and impact events have played pivotal roles in the creation of Martian gems. The study of these processes provides a glimpse into how similar forces might operate across the solar system, potentially influencing gem formation on other celestial bodies as well. Understanding these comparative aspects enhances the broader field of planetary science, revealing the intricate relationships between geology, atmospheric conditions, and the existence of valuable minerals. This ongoing research continues to deepen our appreciation for both planets and their respective geological narratives. Sedimentary processes play a crucial role in the formation of crystals, influencing the development of ruby-like structures on Mars. In this region, fine particles settle over time, creating layers that undergo compaction. These sediments, primarily derived from volcanic activity and weathering processes, provide the necessary minerals for crystal growth. Conditions such as temperature, pressure, and the presence of fluids further dictate how crystals form and evolve. In environments where water once flowed, minerals dissolved and transported, later precipitating as the fluid evaporated. This mechanism contributes significantly to the crystallization of corundum, the mineral family that includes rubies. Specific conditions, such as the high temperatures associated with volcanic events, enhance the likelihood of forming these striking gems. The varying mineralogical components present in the sediments lead to unique colorations and structures within the crystals. Iron and chromium impurities, for instance, impart the characteristic red hue, making each specimen distinct. Geological evidence suggests that ancient Martian rivers and lakes facilitated these processes, capturing the essence of an era when the planet may have harbored conditions suitable for life. Understanding these sedimentary dynamics sheds light on the complex interplay between environmental factors and mineral formation. The implications extend beyond Mars, offering insights into similar processes that may occur elsewhere in the solar system. Ultraviolet radiation plays a crucial role in shaping Martian minerals, significantly influencing their formation and alteration. This region of Mars receives higher levels of ultraviolet light compared to Earth's surface due to its thin atmosphere, allowing for intense exposure. The consequences of this radiation on mineralogy are profound, affecting the surface materials and their chemical compositions. Certain minerals, including the vibrant ruby crystals, exhibit unique responses to ultraviolet exposure. The radiation can induce changes in their crystal structures, leading to alterations in color and luminescence. As sunlight interacts with these minerals, it can trigger photochemical reactions, facilitating the breakdown of compounds and the formation of new ones. These processes contribute to the distinctive mineralogical landscape observed in various Martian terrains. Observations from orbit reveal regions where mineralogical diversity hints at the history of ultraviolet interactions. The resulting chemical weathering may provide clues to past environmental conditions, particularly regarding the presence and stability of water. Additionally, studying these effects aids in understanding how similar processes might operate on other celestial bodies, such as the icy moons of Jupiter or Saturn. The insights gained from the ruby crystals and their response to ultraviolet radiation reveal the intricate relationship between solar radiation and planetary mineralogy, highlighting the role of external forces in shaping the evolution of planetary surfaces. The future of Mars exploration is poised to deepen humanity's understanding of this enigmatic world. Various missions are being planned, each aiming to unravel the complexities of its geology and atmosphere. Robotic explorers will traverse its surface, conducting in-depth analyses of mineral compositions. These missions will not only target the distinctive ruby crystals, but also other mineralogical formations that might offer clues about the planet's history. A focus on sample return missions is gaining momentum. Collecting rock and soil samples to be returned to Earth will provide unparalleled opportunities for detailed examination. Labs equipped with advanced technologies will analyze these samples for organic compounds and other biosignatures, searching for evidence of past life. Additionally, the potential for human exploration continues to be a significant goal. Plans for crewed missions are taking shape, aiming to establish a sustainable presence on Mars. This involves not just exploration, but also the development of habitats that can support life. Technological innovations in life support systems and in-situ resource utilization will be crucial for long-duration missions. Each mission contributes to a larger narrative, painting a clearer picture of Mars's past and future. This endeavor reflects the human spirit of exploration, pushing boundaries in science and technology, while fostering a deeper connection with the cosmos. The implications of ruby crystals for planetary science extend far beyond aesthetic allure. These gems, formed under extreme conditions as dark, reveal critical insights into the geological history of Mars. Their presence suggests significant volcanic activity, where intense heat and pressure facilitated the crystallization of corundum, the mineral from which rubies derive. This region provides a glimpse into the planet's formative years, offering clues about its thermal evolution and atmospheric changes over eons. The study of such crystals aids in understanding the past liquid water activity, which is essential for assessing the planet's potential for habitability. Analysis of inclusions within these rubies may unveil the chemical environment of their formation, shedding light on the interactions between surface materials and volcanic processes. This information can inform models of planetary development, enhancing comprehension of Mars as a whole. In addition, ruby crystals serve as indicators for potential mineral resources. The discovery of these precious gems may guide future exploration missions, targeting areas rich in similar geological formations. As scientists analyze their structure and composition, they also refine techniques for in-situ resource utilization, which is crucial for sustainable human presence on other planets. The unique properties of crystals significantly influence Martian soil chemistry. These formations, primarily composed of silicates and oxides, act as both indicators of geological processes and catalysts for chemical reactions. Their crystalline structures provide insights into the planet's thermal history, revealing information about volcanic activity and past environmental conditions. And the Pansmetris before, Idicea mines, iron-rich minerals dominate the landscape, contributing to the characteristic reddish hue of the Martian surface. These minerals, including hematite and magnetite, play a pivotal role in soil formation and nutrient cycling. The presence of such crystals suggests a history of water interaction. Atrusho is run of past Stvier, which is crucial in understanding the planet's climatic evolution. Geochemical analyses indicate that these crystals may also harbor trapped gases and liquid inclusions, offering a glimpse into the ancient Martian atmosphere. They serve as time capsules, preserving evidence of past conditions that may have once supported microbial life. The interactions between these crystalline structures and other soil components facilitate the release of essential nutrients, suggesting potential for future agricultural endeavors. As in situ resource utilization techniques advance, the extraction and use of these mineral-rich crystals may enhance the feasibility of sustaining human life on Mars. Their significance extends beyond mere geological interest, touching upon the broader implications for exploration and habitation in this hostile environment. The potential for Martian gems introduces a new frontier in space mining, inviting consideration of valuable resources that may be extracted from this arid landscape. These minerals, formed under extreme pressures and temperatures, present not only scientific curiosity but also practical applications for future missions. Deposits of ruby crystals, along with other precious materials, could serve as vital components in various technologies, potentially supporting life-sustaining habitats. This region, characterized by its rust-red dust and rocky outcrops, holds vast quantities of resources that could reshape the economic landscape of space exploration. The extraction of these gems would require advanced techniques, necessitating innovation in robotic and automated systems capable of operating in Martian conditions. Mining operations could become a cornerstone of humanity's presence beyond Earth, facilitating the establishment of sustainable colonies. Interest in these resources is not limited to planetary geology. It encompasses the potential for interplanetary trade. Precious minerals harvested from Mars might find their way back to Earth or be utilized in the construction of spacecraft, enabling longer missions deeper into the solar system. As exploration efforts advance, understanding the distribution and accessibility of these materials becomes paramount. The implications extend to the evolving relationship between humanity and the cosmos. Extend to the evolving relationship between humanity and the cosmos, hinting at a future where the boundaries of our world expand continually. The societal impact of Martian gem discoveries transcends mere scientific curiosity. These findings have ignited a collective imagination, prompting discussions about resource allocation beyond Earth. The allure of ruby crystals, formed under extreme conditions, evokes a deeper understanding of planetary formation and the processes that govern them. Each gem serves as a reminder of the vast potential that lies beyond the terrestrial confines, fostering a sense of stewardship among those inspired by such discoveries. Economic considerations emerge as the prospect of asteroid mining and Martian resource extraction becomes increasingly tangible. The potential for new materials fuels innovation in technology and manufacturing, reshaping industries and economies. This region of Mars, characterized by its unique geological history, may hold the key to sustainable practices on Earth. Cultural narratives evolve alongside scientific advancements. Literature, art, environment, and philosophy begin to reflect a more profound connection to the cosmos. These gems symbolize not only beauty, but also resilience and adaptability, mirroring humanity's own journey through challenges. As exploration continues, ethical questions arise regarding the exploitation of extraterrestrial resources. The delicate balance between discovery and preservation becomes paramount, ensuring that the quest for knowledge honors the integrity of these planetary environments. Such dialogues shape a future where humanity's legacy expands into the depths of space with responsibility and respect. Of mining activities beyond Earth lead to complex ethical considerations that echo the values of stewardship and sustainability. The extraction of resources from celestial bodies raises critical questions about ownership, environmental impact, and potential exploitation. This region of Mars, known for its ruby crystals, presents a unique opportunity to explore these issues in depth. Ownership of extraterrestrial resources remains a contentious topic, International treaties, such as the Outer Space Treaty, stipulate that no nation can claim sovereignty over celestial bodies. Yet, the commercial interest in Martian minerals complicates this framework. These rights and responsibilities require careful navigation to ensure equitable access to resources. Environmental impact cannot be overlooked. Mining operations on Mars may disrupt local geology and potentially harm undiscovered ecosystems. The long-term consequences of such actions must be weighed against the immediate benefits of resource extraction. Sustainable practices should guide any efforts, prioritizing minimal disturbance to the Martian landscape. Collaboration among nations and private entities serves as a vital component in establishing ethical mining practices. Transparent communication and shared knowledge can promote responsible development while fostering a sense of collective ownership of space resources. The path forward hinges on a commitment to ethical principles, ensuring that humanity's reach into the cosmos reflects a profound respect for our planetary neighbors. Such deliberations will inevitably lead to a growing public fascination with extraterrestrial gems. The allure of planetary treasures captures the imagination, igniting curiosity about their origins and potential significance. This interest often transcends scientific communities, fueling a broader cultural narrative surrounding the quest for unique materials beyond Earth. Among these, the ruby crystals of Mars stand out, not merely for their beauty but for their scientific implications. Their formation processes provide insights into the planet's geological history and environmental conditions. Each crystalline structure tells a story of ancient volcanic activity and the intricate interplay of minerals over eons. The vivid red hue, a result of chromium presence, adds a layer of aesthetic appeal that resonates with enthusiasts and collectors alike. These gems symbolize the intersection of art and science, embodying both natural wonder and the potential for technological advancement. Public interest often leads to increased funding for research initiatives aimed at extraterrestrial exploration. This has catalyzed missions designed to retrieve samples from Mars, further fueling the quest for understanding. As missions progress, transparency in findings cultivates a sense of shared discovery, inviting the public to engage with and appreciate the complexities of planetary geology. With each new discovery, the ruby crystals serve as a reminder of the vastness of the universe and the hidden treasures waiting to be uncovered. Art and culture play a significant role in shaping the understanding and appreciation of gemstones, including the ruby crystals found on Mars. The allure of these precious stones extends beyond their physical properties, intertwining with human expression and cultural significance. Various civilizations throughout history have imbued rubies with stories of power, protection, and passion, elevating them to status symbols within their societies. In many cultures, the rich red hue of rubies has been associated with vitality and life force, often linked to mythology and folklore. They have adorned crowns and jewelry, serving as tokens of love and commitment. Artistic representations in literature and visual media often depict these gems as embodiments of desire and valor, enriching their narrative beyond mere mineralogy. This cultural layering creates a multifaceted understanding of what rubies represent, influencing both market value and emotive significance. The study of gemology allows for an exploration of these connections, as experts analyze not only the geological formations, but also the cultural narratives that have shaped their significance. This interplay between the physical and the conceptual fosters a deeper appreciation for the gems themselves and the stories they carry. Through art, the ruby crystals of Mars could one day inspire a new generation to explore the cosmos, linking distant worlds to human creativity and cultural heritage. Meteorological timescales provide a framework for understanding the evolution of Mars, detailing the intricate processes that have shaped its surface over billions of years. This planet, once vibrant with water and geological activity, experienced a series of transformative epochs. Each era reveals the remnants of ancient rivers, lakes, and perhaps even oceans, suggesting a time when life may have thrived in its now barren landscape. The Noachian period, spanning from around 4 billion to 3.5 billion years ago, is characterized by heavy bombardment and the formation of the planet's earliest crust. Subsequent periods followed, marked by significant volcanic activity and the gradual cooling of the planet's interior. The Hesperian era, lasting from 3.5 billion to about 3 billion years ago, witnessed the emergence of vast volcanic plains and the retraction of liquid water, leading to a drier environment. In contrast, the Amazonian period, which extends to the present, showcases a landscape shaped by erosion and the occasional resurfacing from volcanic activity. These geological events have left indelible marks on the Martian surface, creating vast canyons, towering volcanoes, and intricate patterns in the regolith. Understanding this evolution allows scientists to piece together the climatic and geological history of Mars, shedding light on its past and informing future explorations of this enigmatic world. The solar wind interacts with the Martian atmosphere, stripping away particles and influencing surface minerals. This continuous bombardment alters the chemical composition of these materials, leading to significant variations in their properties over time. The absence of a protective magnetic field allows the relentless solar particles to penetrate deeper into the atmosphere, resulting in erosion processes that shape the landscape. Alterations induced by solar wind create a range of mineralogical responses. For instance, the formation of oxidized iron compounds can lead to the characteristic reddish hue of the Martian surface. This phenomenon is a direct consequence of the interaction between solar particles and iron-rich minerals, triggering oxidation and changing their appearance. In this region, Efurcacia anintrisi, the interplay between solar activity and surface minerals offers insights into the planet's atmospheric evolution. Variations in solar intensity can lead to fluctuations in mineral formation, impacting the overall climatic conditions. These processes have implications for the availability of resources that future missions may exploit. The study of mineralogy, altered by solar wind, expands our understanding of Martian geology. It reveals the dynamic nature of this planet, where external cosmic forces play a critical role in shaping its environment. This knowledge not only enriches our comprehension of Mars's past, but also helps to inform potential strategies for human exploration. The influence of cosmic rays extends beyond their initial interactions with Martian surfaces, contributing to the coloration of these remarkable crystals. High-energy particles from distant supernovae and solar flares penetrate the thin Martian atmosphere, bombarding the surface with radiative energy. This bombardment induces various chemical reactions within the mineral structures, leading to observable alterations in color and composition. For instance, ruby crystals, primarily composed of corundum, exhibit a range of hues from deep red to lighter shades influenced by the presence of chromium. When this region is subjected to cosmic radiation, the energy can cause changes in electron states within the crystal lattice. This results in the absorption and reflection of specific wavelengths of light, further enhancing the rich colors observed in these gems. The interaction of cosmic rays with Martian minerals also illustrates the complexity of planetary geology. Changes in radiation levels over time may contribute to varying crystal formations, providing valuable insights into the planet's environmental history. Such data not only informs scientists about the past conditions on Mars, but also aids in predicting future geological processes. Understanding the role of cosmic rays in shaping the characteristics of these crystals establishes a deeper connection between the cosmos and planetary evolution, revealing the intricate interplay of forces that sculpt the Martian landscape. Emerging technologies promise to revolutionize planetary gem research, providing new avenues for exploration and analysis. Advanced spectroscopic techniques enable scientists to examine the unique chemical compositions of minerals on Mars with unprecedented precision. These innovations allow for the identification of even trace elements within the ruby crystals, offering insights into the conditions that led to their formation. And spacecraft equipped with cutting-edge imaging systems can capture high-resolution data from Martian surfaces, revealing the distribution and morphology of these gems across various terrains. Data collected from orbiters and landers facilitates a comprehensive understanding of the geological processes that contribute to the presence of ruby crystals, linking their formation to past volcanic activity and hydrothermal systems. Robotic missions equipped with sophisticated analytical instruments can further probe the physical properties of these crystals in situ. By analyzing their structure and composition directly on the Martian surface, researchers can gather invaluable information about the planet's history and the potential for resource utilization. Collaborative efforts between planetary scientists and material engineers create opportunities to synthesize artificial counterparts of Martian gems in laboratory settings. These efforts enhance the understanding of their formation mechanisms and potential applications in technology and industry. The future landscape of planetary gem research, driven by these advancements, is poised to uncover the mysteries woven into the very fabric of Mars. Collaborative international efforts are essential in the exploration of Mars, uniting diverse expertise and resources to broaden the scope of discovery. Multiple space agencies, including NASA, EASA, and ISRO, are forming partnerships to tackle the complexities of Martian geology and atmosphere. This collective approach fosters innovation, enabling the sharing of technology and data, which enhances the understanding of Mars' surface and subsurface characteristics. Joint missions leverage the strengths of each agency, resulting in a more comprehensive analysis of the planet's potential for past life and resource availability. Instruments developed in various countries are deployed on Martian rovers and orbiters, allowing for extensive geological surveys and atmospheric measurements. This synergy not only improves the scientific yield, but also enriches the collaborative spirit that drives planetary science forward. Data gathered from these missions is made accessible through open-source platforms, promoting transparency and encouraging global participation in Martian research. Collaborative workshops and conferences facilitate an exchange of ideas, spurring new hypotheses and methodologies. As discoveries emerge from these international efforts, they illuminate the planet's history and shape future missions aimed at understanding its potential for human exploration. This united front in the pursuit of knowledge signifies a shift towards a more inclusive and cooperative future in planetary science, revealing the intricate connections between Earth and its celestial neighbor. The ruby crystals found on Mars serve as significant indicators of the planet's formation and evolution. Formed under extreme conditions, these minerals provide insights into the geochemical processes that shaped the Martian crust. Their unique properties reveal the presence of aluminum and chromium, elements critical to understanding the temperature and pressure conditions present during their formation. Examining the crystalline structure of these rubies reveals clues about the impact events that occurred on the Martian surface. Each crystal may encapsulate remnants of ancient environments, preserving a record of the planet's climatic shifts. The study of these gemstones allows scientists to hypothesize the thermal history of Mars, linking geological features to potential past habitable conditions. These findings not only enhance comprehension of Martian geology, but also contribute to broader planetary formation theories. By comparing the ruby crystals of Mars with similar minerals found on Earth, researchers can discern the differences and similarities in planetary development. This knowledge aids in forming models of how terrestrial planets evolve, emphasizing the role of impact events in shaping planetary surfaces. In turn, Unraveling the mysteries of these crystals fosters a deeper appreciation for the dynamic processes at play in our solar system, bridging the gap between planetary science and the ongoing exploration of Mars. Artificial intelligence offers unprecedented capabilities in the realm of mineral discovery, enhancing the efficiency and accuracy of identification processes. Algorithms can analyze vast datasets, recognizing patterns and correlations that would elude human researchers. This technology serves to sift through extensive geological information collected from Mars, identifying potential locations where valuable minerals, such as ruby crystals, may reside. In this context, firstly, machine learning models can predict the likelihood of mineral deposits based on existing geological maps and spectral data. Such predictive analytics enable scientists to focus their efforts on regions with the highest potential yield, optimizing exploration missions. The ability of AI to process and interpret complex datasets leads to a more informed understanding of Martian geology. Collaboration between human expertise and artificial intelligence is particularly beneficial in navigating the challenges posed by Mars' harsh environment. Robotic missions equipped with AI systems can autonomously analyze soil samples, determining mineral content without the need for constant human input. These autonomous systems enhance mission efficiency, allowing for more comprehensive surveys of the Martian surface. As exploration continues, the synergy between artificial intelligence and mineral discovery will likely yield new insights into Mars' geological history. The implications extend beyond the red planet, influencing broader planetary science through refined methodologies and innovative approaches to mineral exploration across the solar system. Predictive models for Martian mineral finding have gained significant attention, offering insights into the distribution and formation processes of ruby crystals. These models utilize a combination of remote sensing data, geological mapping, and advanced analytical techniques to assess the likelihood of mineral deposits. By analyzing surface compositions and mineralogies, researchers can identify areas with the highest potential for hosting these gems. Machine learning algorithms play a pivotal role in enhancing the accuracy of these predictions. By processing vast quantities of data from previous missions, they recognize patterns that human analysts might overlook. This capability allows for the refinement of targeted exploration strategies, reducing the time and resources needed to locate valuable mineral deposits. Geochemical indicators are also taken into account, providing clues about the conditions under which ruby crystals may form. The presence of specific elements, such as aluminium and chromium, can suggest favorable environments for crystallization. These insights lead to more precise geological surveys, guiding rovers and landers toward promising sites. But the interplay of temperature, pressure, and geological processes shapes the likelihood of ruby formation. Understanding these factors contributes to a comprehensive framework that not only aids in Martian exploration, but also enhances the search for similar minerals on other planetary bodies, expanding the horizon of mineralogy across the solar system. The intersection of geology and astronomy reveals profound insights into planetary formation and evolution. This region of Mars, marked by its striking ruby crystals, provides a unique window into the processes that shaped not only the Martian surface, but also the broader mechanisms governing celestial bodies. Geological formations serve as records of past conditions, capturing the intricacies of environmental changes over millions of years. These gems, produced under specific conditions of temperature and pressure, represent the remnants of volcanic activity and the interaction of mineral-rich fluids. Their presence indicates a once dynamic system that may have harbored conditions favorable for life. The study of these formations leads to enhanced understanding of the geological history and potential biosignatures of Mars. The implications extend beyond Martian geology. Similar crystalline structures observed on moons and asteroids hint at shared processes throughout the solar system. The analysis of these extraterrestrial minerals offers clues about the thermal and chemical dynamics of their parent bodies. This cross-disciplinary approach unites astronomers and geologists in a quest to decode the mysteries of planetary systems. Collaborative research enhances exploration strategies, allowing for targeted missions aimed at unlocking the secrets of these fascinating geological phenomena, bridging the gap between our terrestrial knowledge and the vast expanse of the cosmos. The historical significance of rubies transcends mere aesthetic appeal. Cultures across the globe have revered this gemstone, associating it with vitality, courage, and nobility. Ancient civilizations believed that the vibrant red hue embodied the heart's essence, symbolizing love and passion. In Southeast Asia, rubies were often seen as talismans, thought to offer protection in battle and ensure triumph over adversaries. In the Hindu tradition, it was regarded as the king of precious stones, believed to bestow prosperity and happiness upon its wearer. This perception fostered a deep connection between rubies and spiritual practices, linking these gems to divine favor and enlightenment. The enduring allure of rubies is mirrored in their presence in royal regalia, where they adorned crowns and scepters, signifying power and wealth. Plainly adorned crowns and scepters, signifying power and wealth. Trade routes flourished around the quest for these gemstones, influencing economic exchanges and cultural interactions. The vibrant red stones became symbols of status, often gifted between monarchs as tokens of loyalty and allegiance. Artistic expressions, from literature to visual arts, have immortalized rubies in various forms, reflecting their significance in human experience. These cultural narratives continue to resonate, deepening the appreciation for rubies as not only geological marvels, but also as profound symbols woven into the fabric of history across civilizations. The interactions of Mars' magnetic field with its geology reveal complexities that challenge our understanding of planetary evolution. This magnetic field, though weak compared to Earth's, has played a pivotal role in shaping the Martian surface and subsurface. Regions where magnetic anomalies are detected indicate areas of ancient geological activity, suggesting that these locations may have once hosted conditions favorable for life. The variability of this field results from the planet's core dynamics, which remain enigmatic. Studies suggest that the core may be partially liquid, influencing the magnetic properties and, consequently, the geological processes. This interaction leads to the preservation of various mineral formations, including the ruby-like crystals that hint at a more temperate geological past. Volcanic activity, driven in part by the remnants of the magnetic field, has left behind vast plains and towering volcanoes. The Tharsis volcanic region stands as a testament to this history, showcasing the interplay between internal processes and external influences, such as solar radiation. Erosion patterns also bear the marks of magnetic forces, impacting sediment distribution and mineral deposition. Understanding the impact of this magnetic field not only aids in reconstructing the planet's geological narrative, but also informs the search for resources, including those elusive planetary gems that now lie beneath the Martian surface. The future of human colonization introduces complex dynamics regarding the extraction and utilization of these gems. The presence of ruby crystals, formed through unique geological processes, suggests a rich mineral landscape that may offer valuable resources for sustained human presence. Advances in technology will enable efficient extraction methods, minimizing disruption to the delicate Martian environment while maximizing the potential utility of these minerals. The establishment of colonies will necessitate the development of sustainable practices as the need for construction materials and energy resources increases. The extraction of ruby crystals and other essential minerals will likely become a focal point. This region's geological heritage will be tested as humanity seeks to balance resource acquisition with preservation. Ethical considerations will guide the approach to these planetary gems. The scientific community will advocate for responsible practices that honor the history embedded within the Martian crust. Environmental impacts must be carefully assessed, ensuring that the unique characteristics of this mineral-rich landscape are not irrevocably altered. Research will continue to reveal the potential applications of these gems, ranging from technological innovations to contributions in scientific endeavors. As humans establish a foothold, the interplay between colonization and the stewardship of Martian resources will shape the future, ensuring that the legacy of the ruby crystals endures amidst the unfolding narrative of interplanetary exploration. The pursuit of knowledge within planetary science fosters a deeper understanding of the universe and its myriad celestial bodies. Educational initiatives designed to illuminate the complexities of Mars and its unique resources can inspire future generations. These programs engage learners by presenting the intricacies of geology and the formation of ruby crystals, linking theoretical knowledge to tangible phenomena in classrooms and laboratories. The study of impact science offers insights into planetary formation and evolution. By analyzing the consequences of asteroid collisions and their role in shaping Martian landscapes, students cultivate a fascination for the forces that underpin planetary dynamics. This curiosity extends beyond Earth, nurturing an appreciation for the delicate balance of ecosystems across the solar system. Hands-on experiences, such as simulations and field studies, enhance comprehension and ignite a passion for exploration. Collaborative projects enable learners to contribute to ongoing research, bridging the gap between academic inquiry and real-world applications. The cultivation of critical thinking through inquiry-based learning ensures that future scientists can address challenges related to resource management and sustainability. Strengthening interdisciplinary connections among science, technology, engineering, and mathematics subjects creates a holistic educational framework. In turn, this promotes not only individual advancement, but also collective progress in understanding the broader implications of planetary science. Ensuring that knowledge of Mars's ruby crystals and their significance remains vibrant. Engagement with the public plays a crucial role in the ongoing exploration of Mars. Initiatives aimed at connecting diverse audiences with the wonders of the Red Planet foster a sense of shared curiosity and wonder. Through educational programs and interactive exhibits, individuals from various backgrounds gain insights into the nature of these ruby crystals and their formation. This knowledge cultivates a deeper appreciation for planetary geology and the processes that shape celestial bodies. Virtual reality experiences enable participants to simulate the Martian landscape, offering an immersive glimpse into the terrain where these intriguing minerals reside. Such technological advancements transform scientific concepts into tangible experiences, bridging the gap between experts and laypeople. Workshops and community events further disseminate information, allowing families and students to engage directly with scientists and educators. The cultivation of a sense of ownership over planetary exploration encourages ongoing dialogue about the importance of space research. This interactive approach not only informs but also inspires future generations to pursue careers in science, technology, engineering, and mathematics. As interest in Mars grows, so does the understanding of its geological treasures, including the ruby crystals that serve as a testament to the planet's complex history. Through these outreach efforts, the connection between humanity and Mars becomes increasingly profound. Funding for Mars research plays a critical role in advancing our understanding of the planet's geology and history. Financial support enables scientists to develop sophisticated instruments and technologies necessary for exploration. These advancements can lead to the discovery of unique minerals, such as ruby crystals, which hold keys to Mars' past environmental conditions. The allocation of resources directly impacts the scope of missions conducted by space agencies. It ensures that landers and rovers can be equipped with cutting-edge tools designed to analyze the Martian surface and atmosphere. Increased funding fosters collaboration across institutions, allowing for a wider array of experiments and studies to be conducted simultaneously. This cooperation not only accelerates research, but also enhances the quality of data collected from the Martian landscape. Our investment in Mars research also extends to educational programs, cultivating a new generation of scientists and engineers. Exposure to planetary science and impact studies ignites interest in the field. The potential for discovering previously unknown geological formations or organic materials on Mars further emphasizes the importance of sustained financial backing. Each mission contributes to a broader understanding of planetary evolution and the potential for life beyond Earth. This ongoing support for Mars research is vital in unraveling the complexities of our neighboring planet and its implications for humanity's future. The future of space exploration hinges significantly on Mars, presenting both challenges and opportunities that will shape humanity's journey into the cosmos. This region, with its vast plains and towering volcanoes, serves as an invaluable template for understanding planetary processes and the potential for life beyond Earth. Robotic missions have meticulously gathered data, revealing intricate details about its geology and atmosphere. These insights foster advancements in technology, influencing the design of spacecraft and habitats for prolonged human presence. The thin atmosphere, composed primarily of carbon dioxide, provides lessons in resource utilization, particularly in the extraction of water and oxygen. Establishing sustainable living conditions on Mars may pave the way for future colonization efforts on other celestial bodies. Scientific experiments in this harsh environment could unlock secrets of planetary evolution and climate change, offering comparisons to Earth's own history. The presence of ruby crystals and other minerals highlights the geological diversity that exists, suggesting a rich narrative of planetary formation. Collaborative efforts among international space agencies emphasize a commitment to exploring Mars. Shared knowledge and technology enhance the capabilities of missions, enabling deeper investigations into the planet's potential for habitability. Each mission not only expands our understanding of Mars, but also prepares humanity for the broader challenges of interplanetary exploration. Ruby crystals, formed under intense heat and pressure, provide invaluable insights into the geological history of Mars. These gemstones, rich in chromium, reveal information about the planet's past environments and climatic conditions. The presence of these crystals suggests that certain regions may have experienced conditions suitable for life, or at least for the building blocks of life. Their formation requires specific temperature and chemical conditions, which can illuminate the history of water on the surface. In this region, the discovery of ruby crystals implies that significant geological processes have occurred, potentially leading to the development of a more habitable environment. Analysis of these crystals allows scientists to infer the activity of volcanic processes and the movement of tectonic plates. This geological activity is essential for understanding how long-lasting water sources might have existed and whether they could have supported microbial life. The examination of ruby crystals also aids in assessing the stability of Martian atmospheres. By studying the conditions under which these gems formed, researchers can determine how long Mars may have retained its atmosphere and the implications for habitability. Each discovery contributes to a broader understanding of planetary evolution, offering clues not only about Mars but also about other celestial bodies that may host similar conditions. The findings continue to reshape our perspective on life beyond Earth. Recent missions to Mars have provided a wealth of data, unveiling a complex geological history that offers insights into the planet's past environments. Analyzing the mineral composition of the Martian surface has revealed the presence of ruby crystals, formed under high-pressure conditions. These crystals, primarily composed of aluminum oxide with trace amounts of chromium, suggest that Mars experienced significant geological processes similar to those on Earth. The presence of these gemstones indicates that volcanic activity may have played a crucial role in shaping the landscape. Evidence suggests that ancient lava flows, rich in minerals, could have contributed to the formation of these rubies. This region, now characterized by sprawling plains and rugged terrain, once showcased a dynamic atmosphere that may have harbored conditions favorable for life. Through spectral analysis, researchers have identified various minerals and their distributions across the surface. This detailed mapping highlights regions where water once flowed, further emphasizing the planet's potential for supporting life. The interplay of geological and atmospheric factors is essential in understanding the past climate and habitability of Mars. Each new discovery adds another layer to the intricate narrative of its history, providing a clearer picture of a world that was once vibrant with geological activity. In turn, these findings influence ongoing exploration and the search for signs of life beyond our planet. Collaborative research opportunities in planetary science foster a deeper understanding of Martian geology and its unique features. The convergence of expertise from various disciplines enhances the ability to analyze the ruby crystals formed under intense conditions. Such partnerships facilitate comprehensive studies that delve into the processes that created these minerals, revealing insights into the planet's volcanic activity and tectonic history. Interdisciplinary teams comprised of geologists, chemists, and planetary scientists utilize advanced analytical techniques to examine the composition and structure of these gems. This collective approach unravels the complexities surrounding the formation of Martian crust and its evolution over time. Research conducted in laboratories on Earth, combined with data from robotic missions, yields a multidimensional view of the planet's surface. Collaborative initiatives extend beyond individual research institutions, involving international space agencies and private organizations. This shared commitment accelerates the pace of discovery, allowing for joint missions and data sharing. Such cooperation enhances the analytical capabilities required to assess the potential for past or present life, making it possible to identify biosignatures in ancient materials. The implications of these cooperative efforts resonate throughout the scientific community, as they enrich our understanding of not only Mars, but also the broader context of planetary formation and evolution in the cosmos. Each new finding contributes to the intricate narrative of our solar system's history. Formations promise to deepen understanding of the enigmatic Martian surface and its hidden treasures. Scientific teams are already planning expeditions that will utilize advanced rovers capable of traversing the most inhospitable terrains. These robotic explorers will be equipped with sophisticated instruments designed to analyze the mineral composition of Martian rocks and soils, potentially uncovering more of these captivating ruby crystals. Sample collection is a key focus. On-board laboratories will examine samples in real time, while others will be cached for future retrieval. This approach may allow for the identification of organic compounds that could provide insights into past life forms. Enhanced imaging technologies will also play a critical role, delivering unprecedented views of the Martian landscape, revealing the impact of ancient geological processes. Collaborative missions involving international space agencies are likely to amplify these efforts. An increased focus on understanding Martian weather patterns and atmospheric conditions will enhance predictions about how these factors shape the environment. As technology progresses, the prospect of human exploration becomes increasingly tangible. Such endeavors hold the potential to unlock the secrets of Mars, offering a glimpse into not only its past but also the future of human habitation beyond Earth. Each mission builds upon previous knowledge, creating a comprehensive understanding of this distant world. The ongoing exploration of Mars reveals a persistent enigma surrounding the ruby crystals embedded within its surface. These vibrant formations, primarily composed of corundum, suggest a unique geological history that remains largely unexplained. Their striking coloration hints at environmental conditions that may have existed in the distant past, potentially offering clues to the planet's evolution. Scientific analysis continues to uncover the conditions under which these gems formed. The presence of various trace elements indicates complex interactions between molten materials and water. This raises questions about the planet's earlier climate and the potential for habitability. These crystals serve as a record of geological processes, preserving moments in time when volcanic activity and aqueous environments coexisted. Investigations into the ruby crystals also focus on their distribution across Martian terrain. Observations from orbiting spacecraft and surface rovers have identified areas where these gems are more concentrated, suggesting ancient geological events that shaped this region. Understanding their formation and distribution could unlock secrets about Mars's past and inform future missions aimed at uncovering life beyond Earth. The ruby crystals of Mars remain a tantalizing mystery, embodying the interplay of geology, chemistry, and planetary evolution. Each discovery not only enriches our knowledge of this red planet, but also deepens the intrigue surrounding its potential for past life and the ongoing quest for understanding the cosmos.